things we can do at the end of chapter 2. Things we can do. Bump, bump, bump. We should be able to find an average rate of change. So that's this is the very first thing that we talked about this semester. We were introducing ourselves to calculus, right? Here's a function, here is a closed interval over which that function is defined. Tell me what the average rate of change of that function is over the interval. Right? This isn't particularly a calculus question, but once we shrink the change to nothing, that's when it becomes calculus, right? That's when it becomes a derivative. So this is where we started, and it's what we would like to do. It's worth noting a couple of things just in terms of context here. That the average rate of change corresponds to the slope of a secant line. Okay. So here's kind of the geometrical interpretation of an average rate of change. The reason I introduce it here is because we'll have a geometric definition for the derivative, for the instantaneous rate of change. And what's happening is that these dots are getting closer and closer together so that you wind up with a tangent line. So it's worth remembering that that falls out of thinking about a derivative from an average rate of change perspective to begin with. All right. Also, so we decided that we wanted to kind of push these together, and we were introduced, going crooked here, to limits. Right. So limits are big. I will not force you on the exam to kind of plug and chug at any time. So there's not going to be an instance where I say something like, oh, I want you to find the limit as x approaches 0 of this expression, so just plug in numbers and then guess. Because I don't think that's an appropriate method. It's kind of what's happening, right? We are looking to see kind of a pattern of like what this is headed toward, but those numbers and our calculators may trick us, as we found in examples. There's a good example in the homework that kind of pointed that out. So that way of estimating the limit will not be one that we see on the exam. But we may see other types of things, right? So the easy one is using continuity, right? Remember that continuous functions are the ones that are defined in such a way that the limit and the function are always the same. So if I had something like the limit as x approaches 0 of e to the x, right? E to the x is a continuous function, and it's continuous at 0, so I can just plug 0 in and tell you that that's e to the 0, which is 1. Right? But we also saw examples where we simplified. So things like the limit as x approaches 0 of e to the x minus 1. This is a bad example. About x squared minus 1. I was going to try to keep it into a family, but let's not. So x approaches 1 of x squared minus 1 over x minus 1. Okay. Now if I just try to plug and chug, right? X squared minus 1 is a continuous function. X minus 1 is a continuous function. The quotient of two continuous functions should be continuous as long as the bottom's not 0. But then when I plug 1 in, it looks like 0 over 0, and that's indeterminate. indeterminate, a very long word, and just barely fits on the screen here. But it looks like 0 over 0, that's indeterminate. But that doesn't mean that the limit doesn't exist, right? Instead, I can try to simplify this expression, cancel any like factors, and then evaluate the limit, and I see that it's 2. So this is an algebraic way that we might evaluate a limit through simplification. Also, using graphs. So we might see a picture of a function. Right? And I might say, evaluate the limit as x approaches -1 from the left. The limit as x approaches -1 from the right. The limit as x approaches 0. Okay. So evaluate all these limits, and here's a picture of the function instead of telling you algebraically what the function is, like I might up here. So those are skills that we have. This introduces the idea of one-sided limits down here for graphs. So be familiar with this notation. What happens as we approach -1 from the left? What happens as we approach -1 from the right? One-sided limits are kind of tied to continuity in a couple of different ways. Primarily, one-sided limits are at first telling us whether a limit exists, right? So for instance, in this graph I've drawn, the limit from the left is approaching 1 point, and the limit from the right is approaching a different point. One of these might be empty, and the other circle might be filled in, so that it's a function. Okay. And because the limit from the left is not the same as the limit from the right, we would say that the limit does not exist. But there are examples where the limit from the left exists and the limit from the right exists and is the same. So the limit exists, but the function is defined to be something completely different. And that's going to result in a continuity problem here, right? If I were tracing this, trace, got to pick it up, hit this dot, pick it up, come back down and hit it. Right, so there will be a discontinuity here. This is sometimes called a removable discontinuity or a hole. Usually a hole refers to the situations where the function isn't defined there and there's just a hole. So this is kind of removable. You could pick this dot up, right, remove this dot, and then fill it in somewhere else. And you have a continuous function. So that would be great. Would fix your issue. Let's see. What else have we discussed? We talked about instantaneous rates of change next. Right. Instantaneous rates of change, which we interpreted as the slope of a tangent line. And we later found out was this thing that we called the derivative. So these three concepts are all really the same. And you should be able to talk about them interchangeably. Right? So you might be able to look at a geometric picture of a curve and talk about the slope of a tangent line and know that that's the derivative. Or you should be able to look at a geometric representation and say, oh, well, the slope of this tangent line is going to be the same as an instantaneous rate of change in application, right? So if that curve is, say, measuring cost, and I wanted to know what the instantaneous rate of change for that cost was, Right? It corresponds to the slope of the tangent line. Similarly, if I tell you that c of x is cost, that you should be able to interpret c prime of x, the derivative, as the instantaneous rate of change. So we should be able to kind of move between these three ideas interchangeably and be able to interpret results. So we might see things where I ask you to find the units for a derivative or explain in a sentence what an expression that involves a derivative means. So if I say something like c prime of x equals 100, right, or c prime of 3 equals 100, I might give x a value. Okay. What does that mean in the context of cost, if c is measuring cost? Okay. What are the units for 3? What are the units for 100? Okay. And this is the language of derivatives, but I'm asking you questions about an instantaneous rate of change. So that is a value. We saw plenty of examples of that in the text. We saw things like graphing derivatives based on the function. Right? So graphing derivatives is important, right? Being able to interpret information about f prime of x from the graph of f of x is important. As far as instantaneous rates of change, a particular example of interest is if s of t is position along a line. Right? You'll remember that s prime of t is velocity, and that s double prime of t is acceleration. So those are of interest. Okay. This brings in the idea of higher derivatives. Right? So the second derivative, right, we might be interpreting that geometrically or in application. Right? It's going to correspond to acceleration if s is position. It tells us the rate at which the rate of change is changing. And geometrically, it's going to correspond to how the graph is curving. Right? Is it curved up? Is it curved down? If the second derivative is positive, then it'll be curved up, and if it's negative, it'll be curved down. Other notations, right? So you should be familiar with f prime of x, y prime, y double prime, f double prime, dy dx, d dx of f of x, things like this. D squared y dx squared. Right? All of these are different notations for the first and second derivatives. And you should be comfortable using these interchangeably. I will not be asking you at any time in this course to use one exclusively, but I may use either interchangeably, and you should be able to see what I have written and interpret it correctly. So that's kind of the important thing here. When I was an undergraduate, I took Latin as a foreign language, and in part because I'm incredibly lazy. And when I took Latin, we neither had to speak Latin, hear Latin spoken and interpret it, nor did we ever have to look at an English expression and translate it into Latin, because people don't really do that anymore. Instead, we were always looking at Latin and needing to interpret it into English. Okay? So that's kind of the idea here, right? I need to be able to use these interchangeably and have you understand them, but I'm not going to force your hand and make you use one or the other. Right? I'm not going to make you speak in Latin if you don't want to, but you know, if I write something in Latin, right, you might be expected to know how to read it. All right, so all of that is valuable. What else do we have here? Nothing else is really springing to mind. Are there any of these topics that you would like me to kind of expound upon? Right? Anything that's seeming rusty? Any homework problems from chapter 2, right? So if you want a good idea about the types of things that I want you to be able to do, right? Remember, we're in chapter 2, so all recommended exercises are good examples, right? If we've seen an example in class, most of which is available on YouTube in the links provided on Blackboard, or if I have assigned an exercise that I'm recommending you to be able to understand, those are all kind of like good ideas about the type of thing that we should be able to kind of contend with on an examination that is designed for us to demonstrate our understanding of the topic. Okay? I like to think of it that way, right? Not as kind of like this kind of like tense test that you kind of have to come out the other side of, but right? It's an opportunity for you to tell me what you know. Right? Oh, I think I know derivatives. Let me show off so that Dr. Clark's impressed with me. Not that you should, you know, be overly concerned with my impression, but has lower stakes attached to it if you think of it that way, I guess. So, is there anything like that that people are concerned with? All right, let's then look at a kind of concept test question, right? Just to kind of gauge our understanding and for me to kind of see where we might be. So. I'm going to make up a function here. I don't know what it might look like, right? Functions can do anything. And then up here, and then I might do something like this. And then, I don't know, what are things that we can do? Just gonna come back up. So here's a weird function, and I'll give it a name, y equals f of x. All right. And then I might give us a list of expressions, and I will ask you whether that expression is positive, negative, zero, or non-existent. D&E does not exist. And we might see things like f of 0, f prime of a half, f prime of 1, How low am I getting here? Right? F prime of 2, F double prime of 1, F of 3, F prime of 3, F prime of 1, 2, 3, 4, 5, F prime of 5. F prime of 6, F double prime of 6. These shouldn't take too long, right? Yeah.
Maybe turn off the one line so maybe it'll be
Yeah.
easier to read that.
Let's try to make it easier to read here in the class. Does that help? Maybe.
I
Let
just can
me-
adjust on some of it, whether it's prime or double prime.
Okay. Yeah. Sorry, my this might help. And so nothing, prime, 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 double prime here for the for this one, and then F by itself, F1 prime, 1 prime, 1 prime, and the last one is double prime. So there are 2 double primes in there. I'm gonna add a couple more. F double prime of 3.5. That's 11 problems. But these should run really, really fast, right? These are things that we should be able to interpret almost immediately from the graph of this function. Right? Everybody have it copied down? Anybody still writing? All right, so let's have at it. F of 0, is it positive, negative, 0, or does not exist? I'm hearing contending responses. I heard positive, I heard 0. Anyway, who's in the positive train? Who's in the 0 train? Bunch of undecided. I think the zeros are having it. Why? Can a 0 representative tell me why 0? Yeah, so the at 0, if x is 0, right? F is the height of the function, right? So the outcome is 0, right? It's on the x-axis. It doesn't have any height here. And that's what F is measuring, right? This point is 0, 0. And so if x is 0, y is also 0. So that's 0. What about f prime of 1/2? Positive, negative, or 0?
Positive.
That's overwhelmingly positives from the peanut gallery here. Why positive? Yeah, the slope is positive here, right? This is an f prime, and x is 1/2. X 1/2 is here, right? This little guy. And so the point it's corresponding to is about yay. And remember that f prime is measuring the slope. So that slope is positive. It's increasing at that time. The function is increasing, and so that's a positive derivative. What about at 1? I think the zeros are starting to be convincing, right? So it's flat kind of at that time. It's at the peak of that hill. So the slope is 0 there. What about at 2? That's here. X is 2 here. So f prime of 2 corresponds to this time when x is 2. Yeah, the function is decreasing there. And so the slope is negative. So negative. Looks like we're rewinding to 1, right? We did f prime of 1. F prime of 1 is 0. What about f double prime of 1? So that's here. What geometrically, what is the double prime all about? Right? It's the derivative of the derivative, right? And it's measuring the change in the derivative, and it's telling us curve, right? So whether the second derivative is positive or negative is telling us whether the first derivative is increasing or decreasing, and whether that rate of change is increasing or decreasing is going to curve the function different ways, right? So if the first derivative is decreasing, we're going to get like a frown type of thing. The second derivative will be negative. And if the second derivative is positive, then the first derivative is increasing. We get increasing slopes. So we kind of wind up with like a cup. Yes?
So it's just referring to concavity.
Just the concavity. The second derivative only corresponds to the concavity. And what's the concavity at this point? Is it concave up or concave down or no concavity?
Down.
Yeah, concave down. And so concave down tells me positive or negative? Negative, right? You can see that kind of at this time, the slopes are decreasing, right? Decreasing slopes is going to be concave down. So that's a negative second derivative. What about f of 3? Two is here. It's kind of hiding now.
Wouldn't it be that point below it?
Yeah, it's the point. Yeah, exactly. It's negative. Remember, f is corresponding to what the outcome is. It's just what the y value is, right? F is always where, right? X is 3. The outcome will be this point, right? So f of 3 is this distance. So it's negative because it's below the x-axis. What about f prime of 3?
0.
That's 0, right? Because it's corresponding to the slope here, right? How steep is the curve at that time? What's the slope? I didn't put it here, but what about f double prime of 3? It does exist. We didn't talk about this a lot in class. Just to the left, right, it's concave up, so it's going to be positive. And just to the right, it's concave down, so it's going to be negative. If you were traveling from positive to negative, you've got to pass through 0. So this is a place where the concavity is 0. These places where the concavity of a function changes, they have a special name. We call them inflection points. Right? So if the concavity of a curve changes, then it's called an inflection point. And that is an example of one, right? Where it's concave up and then it's concave down immediately after. So it's going to be 0 in between. All right. That's a little addendum. What about f prime of 5? So 1, 2, 3, 4, 5. Here's x equals 5.
Negative.
It could be negative. I wasn't really going for a negative here.
Well, if you're thinking at that top part, it's pretty horizontal, and then it goes down.
Right. So I'm thinking at 5 is this point. So the tangent line is this one, right? It's a vertical line. So what is the slope of a vertical line? Slope of a horizontal line is 0, right? We saw 0 here and here. And this is the DNA. So this is an example of what it might mean for a derivative not to exist. Here's an example of another time where a derivative won't exist. So now, if I wanted to do something like f prime of 7, right? 7 is out here. Right? The slope here doesn't exist because it's pointy. It's a little cusp. So f prime of 7 would be another example of a time where a derivative did not exist. Right. What about f prime of 6? Also 0, right? So the 0 derivatives can be peaks or valleys or neither. But these places where the derivative is 0 all correspond to the tangent line being flat, right? It doesn't mean that it's a maximum relative to the point that are around it, or that it's a minimum relative to the points around it. It could be neither, right? This is neither a max nor a min, respective to the things that are around it. It's just kind of right in the middle. The function takes a break there. It doesn't change for a moment, and then it continues changing. So that's worth noting that that could happen. What about f double prime of 6? Ooh, some contention. Positive, right? Yeah, right. It's concave up like a cup, right? And so the concave is up, so it's positive. What about f double prime of 3.5? Where's 3.5? Here's 3. So 3.5 is just to the right. So we're here-ish. Yeah, negative, right? It's concave down. So that's negative. Notice that it's decreasing here, but it need not have the other part of it. It doesn't have to have like the whole frown. It could just be part of the frown, and it's concave down. You can be concave down and increasing, or you can be concave down and decreasing, right? Concavity doesn't have anything to do with whether a function's increasing or decreasing, only with the way that it's curved. Here's concave down and increasing, here at 0.5. And here's concave down and decreasing, over here at 3.5. So, again, just to kind of reiterate, f is where, f prime is how steep, right? This is slope. And f double prime is concavity, right? It's the curve. Right? And none of them determine exactly any of the others, right? F prime is increasing, decreasing. Right? You can be increasing or decreasing, and that doesn't tell you where it's happening, and it doesn't tell you whether the concavity is up or down. It just tells you information about f prime. Similarly for concavity, it can be concave down, but it could be increasing, or it could be concave down and decreasing. It could be concave down and high up on a function, or it could be concave down and low on a function. Right? F double prime will not dictate the behavior of f or f prime. Like at a point. Questions about this? If this were a lot of the exam, people feel really confident that they'd be able to do this type of thing in general, interpret the results. Right. That's good. There will be something like this on the test, right? Whereas here's a picture, just kind of tell me whether things are positive, negative, or neither, or whether they don't exist. I like this type of problem.